right, here's some of our force calculations actually start to get a little bit interesting, because we are parking a car on a street which has got an angle to it. So we have an inclined plane. The easiest way to do this is to tilt our reference axes, and now you'll see why I've made you draw your little I and J axes as your reference axis every time. Let's have a look. A car of mass 800 kilograms is parked in a street which has an angle of elevation of 15 degrees. The car is subjected to 3 forces: weight, normal contact, and applied force of the brake. Calculate the magnitude of the normal contact force and the magnitude of the applied force of the brake. Okay, now I'm going to draw the street in. There's my street. Okay, and I've got a car parked on that street. Let's make it parked over here. We're going to represent it as a point. All right, now we know that the weight force always acts straight down. Doesn't matter what incline anything's at, my weight force always acts straight down from the object. However, my normal contact force always acts at 90 degrees to the surface that is being contacted or rested upon. Okay, and my brake force has to be happening parallel to my street, because that's holding the car up and stopping it from slipping back down. So this is my brake force here, parallel to my street. Okay, now we've said that our street has an angle of elevation of 15 degrees. So let's put that in there. So it means that this angle here is 15 degrees. Now the interesting thing about this, and we can do the proof at some stage to find, just with Euclidean geometry, how this is, but basically whatever your angle of elevation is going to be the same angle with your weight force acting down. All right, and that then allows you to resolve your different forces into I and J components. But now notice, it doesn't really make sense to use the normal I and J components as a reference, because it almost looks like everything has been twisted. So why don't we just twist our axes, and then there are fewer forces that we have to resolve. So I'm going to say that this is now what my reference axis looks like. So this is I and this is J. So I'm just tilting everything by 15 degrees. Okay. So it's almost like you're now tilting your head and pretending that everything is on a normal XY plane along the same plane as the road that you're working on. Okay, so let R be the resultant force in newtons. We're going to let W be the weight force in newtons. We're going to let N be the normal force, and let F be the braking force. Okay, I've defined all my variables. And we now know that this car is parked. If my object is stationary or moving in constant motion, my object is in equilibrium, which means my resultant force is equal to 0. Okay, so I'm going to say car is in equilibrium, therefore R is equal to 0. Okay, it's really important that we're writing that, okay? All right, so let's see what each of these are. So R is 0I plus 0J. My normal force is the easiest one to do now because with my twisted axis, it is just acting in a positive J direction. So that's just going to be NJ. Now my weight force is a little bit more challenging because I've got an angle. However, this is my J axis and this is my I axis. So I've twisted it, okay, and this is my angle. So in my negative I direction, I have a sine ratio, and in my negative J direction, I have a cos ratio. So I'm going to have negative W sine of 15 degrees I minus W cos of 15 degrees J. Now, my W is just going to be mg, and that's going to be 800 times 9.8. So I'm going to have minus 800 times 9.8 sine of 15 degrees I minus 800 times 9.8 cos of 15 degrees J. So that's what my weight force is going to be. And my applied braking force, well, that one's quite easy to do as well because it is now just in my positive I direction. So F is going to just be Fi. All right, and we know that R, my resultant force, is going to be N plus W plus F. So I can add it all together. And I think I'm going to run out of space. Let's shrink this a little bit. And maybe put a line down the middle there. Okay, it looks better. So I have 0I plus 0J is equal to N minus 800 times 9.8 sine of 15 degrees. NJ I minus 800 times 9.8 cos of 15 degrees J plus F, and I can collect all my I and J components, so 0I plus 0J will be, and that's an Fi, minus 800 times 9.8 sine of 15 degrees plus F I plus N minus 800 times 9.8 cos of 15 degrees J. And hopefully you can see immediately where I'm going with this because I'm going to equate my I and J components. What I get is that 0I is negative 800 times 9.8 sine of 15 degrees plus my F, So F must be equal to 2029.1 newtons, and I'm supposed to have an I there. My J components 0 is n minus 800 times 9.8 cos of 15 degrees. So my N, or my normal contact force, is 7572.9 newtons. So therefore the normal force is approximately 7573 newtons, and the braking force is approximately 2029 newtons.